We are in chapter 3 where we are discussing torsion. This is the 16th session overall. Within torsion, this is the fourth and last session. Here we will be discussing thin-walled hollow members and solid non-circular members. In this map involving the first 4 chapters of mechanics of materials, we see that we are at the end of the third chapter, that is the chapter on torsion. This last session in torsion involves non-circular members subjected to torsion. Here we looked at thin-walled hollow members subjected to torque. Till now, the discussion has been on circular bars and circular tubes subjected to torque. These members were axisymmetric, and we could find out the variation of strain, and then using Hooke's law we found out the variation of stress. We then related stresses in a section to the internal torque. This was given by the torsion formula. We now obtain an expression of stresses for thin-walled hollow members. So this is the member. Cross-section can be any arbitrary cross-section. Also, the thickness of the thin wall can vary. However, the thickness of that wall has to be quite small compared to the cross-section and also to the length of the member. Here we consider a torque acting on the right end and a reactive torque on the left end. Let us consider two perpendicular cross-sections, that is perpendicular to the axis, at infinitesimal distance apart, as shown here. We will consider the portion LMOP, whole bar being in equilibrium. The narrow portion between the two cross-sections will be in equilibrium, and also the portion LMOP will be in equilibrium. A magnified diagram of the portion is given here. This diagram is three-dimensional, and LM and OP coincides with the x direction. So LM here and OP coincides with the x direction. At LM, let us consider the thickness of the thin-walled hollow member is TA. At OP, let us consider the thickness of the thin-walled hollow member to be TB. The width is dx of this portion. Let the shear stress acting on LL-MM- be tau A, and the shear stress acting on the opposite end PP-O be tau B. Now from equilibrium, summation Fx is equal to 0. So Fa and Fb has to be equal to each other. which means tau A PA into dx, that is the force FA, has to be equal to tau P into PP into dx. This means that tau A into dA has to be equal to tau P into PB. While dealing with elements subjected to shear stresses, we saw that either the shear stresses emanate from a corner or they act towards a corner. Also, the magnitude of the shear stresses are equal in the perpendicular directions. So let us consider that M dash is the corner of an element. Then since tau A acts away from M dash, around the corner there would be a stress tau A that will also act away from M dash. Let us also consider that OO dash is the corner of an element. This element is quite different from the element of which MM dash is a corner. But at the corner of OO dash, since this shear stress acts towards OO dash, the perpendicular shear stress will have the same magnitude and act towards OO dash as shown. If we multiply the shear stress with the thickness at MM dash, then we get tau A into dA. Similarly, if we multiply the shear stress at OO dash into the thickness, we get tau P into PP. However, we earlier saw that tau A into PA is equal to tau P into PP. Hence, we can say as we move around from in a MO, the multiplication of shear stress into thickness is a constant. The multiplication of shear stress into thickness is referred to as shear flow and is denoted as Q. We could have taken this small area LMOP in any different part of the strip, that is the strip between the two cross sections taken. So it could have been somewhere over here or somewhere over here. The shear flow has to be the same. So if we consider the cross section of which MO is a part, the shear flow stays the same throughout the cross section. So here we have shown a diagram of the cross section. This section is perpendicular to the axis of the member. The shear flow will remain the same. There's an inner wall and an outer wall, and the shear flow will not depend upon where the thickness is small or where the thickness is more. We can think of this cross section as that of a water channel with an outer wall and an inner wall and of constant depth. So the depth of the water channel is the same throughout. Then we will expect that in the wider part of this channel, the velocity of water will be less, while in the thinner part of this channel, the velocity of the water will be high. The velocity of water multiplied by the width will be a constant. So the water flow will be constant. Here, shear stress into thickness is a constant, and the reason for us calling this product as a shear flow is due to its analogy with water flow. This diagram shows the cross-section area perpendicular to the axis of a thin-walled hollow member subjected to torque. We earlier discussed such a cross-section, and we found out that the shear flow along the cross-section will be the same. Let us consider this as the outer wall and this as the inner wall. Here we have also drawn the center line of the cross-section. Let us consider a small element of length ds, where the length ds is along the center line. Let P be the thickness of this element and tau be the shear stress acting. Due to the shear stress, there will be a small force dF, which will be given as shear stress into the area. So dF will be equal to tau P into ds. Now tau into T is the shear flow. So dF can be written as Q ds. Let us consider a point O somewhere in the cross section. Then the force dF will create a moment about the point O, and the moment will be given as dF into PO, where PO is the perpendicular distance. So if we refer to that moment as dm, then dm is equal to dF into PO, but dF has earlier been given as QDS. So dm is equal to QDS into PO. Now let us look at the area of the triangle APO. Area of the triangle is given as half base into height, that is half S into PO. Here we see that ds into PO is common in these two cases. So dm can be given in terms of the area of the triangle APO. dm is given as 2q into area of the triangle APO. Let us consider a small element adjacent to the element given here. It will also cause a small force about point O. The small force will create a moment which will be given as 2q into the area swept by the arc corresponding to that force. Other small areas can create small forces, and as such moments can be created which will be given as 2q into the areas swept by the arcs corresponding to that force. There are forces acting all over the cross-section which will create moment about the point O. So the overall moment created will be 2q into the whole area under the center line. This moment comprises the internal torque. So P is equal to integration dm is equal to 2q into A, where A is this whole area. So shear flow can be given as equal to the internal torque divided by 2 into the area within the center line. Or shear stress tau is equal to E divided by 2 small t into A, where small t is the thickness of a particular section and tau is the corresponding shear stress at that particular section. We look at two examples involving thin-walled hollow members. In this example, the thin-walled hollow member is in the form of a rectangle. The width of the vertical sides and the horizontal side differ. We are given the torque that is applied and we are required to find out the stresses. In order to find out the stresses, we first of all draw the center line of the section. As one would recall, we are required to find out the area within the center line to give us the stress. Now let us look at the dimension of the center line along the horizontal direction. Then the dimension would be given by this width of the section minus half the thickness on one side and half the thickness on the other side. So the horizontal dimension is given as the total width of the section minus the thickness. Similarly, the vertical dimension of the center line will be given as the total vertical dimension of the section minus the thickness. So we multiply those to get the area within the center line. Knowing the torque, we find out Q or the shear flow. To find out the stress on the horizontal side, we divide Q by the appropriate thickness and we find the stress. Similarly, to find the stress in the vertical side, we divide Q by the appropriate thickness. This is another problem involving a thin-walled hollow member to which a torque has been applied. We are required to find out the stresses on the side AP and ED. So first we plot the center line of this thin-walled hollow member. We have to find out the area within the center line and we can find it out using three portions. So A, B, F is the quarter of a circle. AFGE is a rectangle and BCBG is another rectangle. So if we add these three areas up, then we'll get the area within the center line. Now the radius of this quarter of a circle to the outer is 45 millimeter. So the distance from the center line would be 43 millimeter. This distance is 75 millimeter. Take 2 millimeter on this side and take 4 millimeter on the bottom side. Then the distance of the center line would be 69 millimeter. If this distance is 69 millimeter, then the distance ED will also be 69 millimeter. Now we can see that distance AF is 43 millimeter, or the distance EG is also 43 millimeter. So the distance BC or GT would be 26 millimeter. We can now find the area of the three portions. So the area of this quarter of a circle is pi into r squared divided by 4 plus the area of this rectangle is this dimension multiplied by this dimension plus the area of AFGE is this dimension multiplied by this dimension. We are given the torque, so that torque is equal to 2 area within the center line into Q, from which we find Q. In AB, the thickness is 4 millimeters, so the stress is Q divided by 4, and we find the stress. And in ED, the thickness is 8 millimeter, and again we find the corresponding stress. It was only for a bar of circular section that a relation between stress and torque could be given. This is not generally applicable. For solid non-circular members, such as a member with a rectangular cross-section or a square cross-section, a compact formula cannot be given. When torque is applied to bars of such sections, then plane sections do not remain plane, and there's a distortion within planes. For a square cross-section, when a torque is applied, all sections get warped. It is only a line through the middle of the surface that stays straight, and a line connecting the corners, that is a diagonal connecting the corners, which remain straight. Here we have a rectangular section on which torque is applied. If we take a cross section as shown, then the maximum stress that occurs on the section will be at the midpoint of the larger side. So this line, which joins the midpoints of the larger side, has the maximum stress if any section is taken. Here the stress distribution has been shown along only three radial lines. So this line, and this line. We see that at the corner the stress is 0. For a rectangular section, at all corners the stress is 0. This is because there are extra free surfaces on the corners where the stress has to be zero. This is different from an element on a circular bar. We have shown here an element on the surface. This element always has an adjoining element to it. Maximum shear stress and the angle of twist in a rectangular bar has been given using mathematical theory of elasticity. So tau max is equal to T divided by alpha BC square, where B is the side with the larger dimension and C is the side with the smaller dimension. The angle of twist phi is equal to TL divided by beta B C Q G. Here alpha and beta are coefficients that has to be found using a table or using a formula. For B divided by C less than 5, we have to use the table. For B divided by C greater than 5, we can use the table or we can use this formula. Now alpha and beta for B divided by C greater than 5 are equal. For large values of B by C, both alpha and beta can be taken as 1/3. The stresses on a rectangular section subjected to torque can be given using a membrane analogy. Consider this frame and a membrane attached to it. Let us consider that there's a pressure acting on this homogeneous membrane that gets the membrane bloated as shown. The partial differential equation that governs the behavior of this membrane is the same as the partial differential equation of a rectangular section subjected to a torque. Consider a point M on the rectangular section. We can find the point M dash that corresponds to the point M in the membrane. We need to find a line which has a slope that is horizontal and passing through the point M dash. The direction of this line is the direction of the shear stress at M. Also, we can take different straight lines passing through M dash and find out the line which has the maximum slope. The slope of this line is proportional to the stress acting at M. For this bloated membrane, we find that the slope at N dash is the maximum slope considering all the points. N dash is the middle of the largest side. This matches with the fact mentioned earlier that the maximum stress for a rectangle subjected to torque is at the middle of the larger side. Now this frame and the bloated membrane encloses a volume. We found that this volume and the torque applied on the rectangular section are proportional. We earlier discussed membrane analogy with respect to a rectangular bar. A frame of the same section as the bar was taken and a membrane stretched over it. The membrane was subjected to pressure, and the bloated membrane was used to find the direction and magnitude of shear stresses in the rectangular bar. The volume between the membrane and the frame was found to be proportional to the torque applied. In general, any cross-section can be taken. A frame has to be the same as the cross-section. A membrane has to be stretched over this frame and subjected to pressure. Then, as previously, we can find out the magnitude and the direction of shear stresses using the bloated membrane. Here we have three thin-walled structures which has the same centerline length and thickness. Hence, the area of these structures are the same. If a membrane is bloated over these structures, then the volume will be the same and the maximum slope will be equal. Hence, if the same torque is applied to these structures, then the maximum stress will be equal. We can use the structure here at A to find out what the maximum stress will be. So here B will be quite large and C is small, so B divided by C will be quite large. As such, alpha and beta will both be 1/3. Here an example is shown. This is a rectangular bar and the dimensions of the bar are given. The maximum allowable stress is given and G is given. We are asked to find out the maximum torque that can be applied and the corresponding angle of twist. So here, first of all, we find B divided by C, and using the tables, we can find alpha and beta. Since we know the maximum stress, we can find out the maximum torque that can be applied. Knowing the maximum torque, we can use the equation of phi to get the angle of twist. Here we have an example of torque and angle of twist involving a square and a circular bar. The area of the square bar A is considered to be equal to the area of the circular bar B. The lengths are the same and the maximum shear stress in both bars are considered to be same. We are asked to find out the ratio of the angle of twist of these two bars. To find the ratio of the angle of twist, we first find out the torque applied in both these bars in terms of the maximum shear stress, which is constant, as well in terms of dimensions of one of the bars, since the cross sections of both these bars are the same. We choose the dimension of the square bar for representing the dimensions of both the bars. Since the square bar has B divided by C is equal to 1, using the tables we can get alpha and beta. Then tau max is given by this formula. Here B and C are equal, and we get the expression of tau max in terms of Ts, or the torque in the square section. When it comes to the round section, we first convert the radius of the round section in terms of the side of the square bar. So the area of the square bar is b square, and the area of the round section is pi r squared, from which you get a value of r in terms of b. Now for a circular section, tau max is equal to tr by j. Here j is pi r to the power 4 divided by 2. So we write r to the power 4 in terms of b, as well as r on the numerator in terms of b. And from there we get the value, get this expression of tau max. Now tau is the same in both the bars. So here we have written Ts in terms of tau and b for the square bar. And here we have written T r in terms of tau again and b. Now for the square bar, phi is given by this expression. Now b for the square section we have found in terms of tau and b, so we can replace that b. C here is equal to b, and beta for the square section we have found. So replacing all that, we get the angle of twist as tau L divided by 0.676 GP. The angle of twist of a round bar is given as TL by G into J. So again here we replace T in terms of tau and B that we obtained earlier, and J in terms of B that we again obtained earlier, and we get the angle of twist as tau L divided by 0.564 GP. Then dividing the angle of twist of the round bar by the angle of twist of the square bar, we get the ratio of the angle of twists as shown. Here we deal with thin sections. Earlier, based on membrane analogy, we discussed that thin sections can be treated like thin rectangular bars, or bars with thin rectangular sections. Here a standard section is taken as mentioned. The thickness and the area of the section is given, maximum allowable stress is given, and G is given. We are asked to find out the maximum torque that can be applied and the corresponding angle of twist. We can find the distance of the center line by dividing the area by the thickness. So once we know B, we can find out B divided by C. The value obtained is larger than 5, and we can use the equation for both alpha and beta, from which we get the values of alpha and beta. We are given the maximum shear stress. So with alpha known and B and C known, we can find out the maximum torque that can be applied. Now with the maximum torque known and beta, B and C known, we can find out the angle of twist as shown. Here we have the case of an I section that is subjected to a torque. We are not given the torque. We are given the maximum shear stress that can be applied. We are asked to find out the torque and the angle of twist. Now consider the straightforward case where we are given the value of the torque applied. Then we can see that the torque is equal to twice the torque taken by the flange and the torque taken by the web. We do not know the torque taken by the flange and the torque taken by the web, so we have two unknowns. However, we have only one static equation. The other relationship comes from deformation, since the angle of twist of both the flange and the web will be equal. So we will be able to find for the torque in the web and the flange using the two equations. Here, however, the situation is different since we are not given the torque that is applied, but we are given the maximum stress. However, using the deformation relationship, we can find a relationship between the torque in the web and the flange. We can then find the maximum torque that the web can sustain and the flange can sustain. Since we have the ratio of the torque in the flange and the web, we can find out which one will fail first. We can then find the whole torque that can be applied without failure and the corresponding angle of twist. So here, first we find out the relationship between the two torque in the flange and the web using the angle of twist. We have used a standard I section and we know all the dimensions of the I section. We start with the flange, so we know B and we know C. B by C is greater than 5, and we find alpha and beta using the equation. We then find phi flange in terms of the torque in the flange, or TF. We have substituted the value of beta and the other dimensions here. We now look at the web. We can find B and C, which we find to be greater than 5. So we find alpha and beta using this equation. We then find the angle of twist of the web in terms of Tw, or the torque in the web. Since the angle of twist in the flange and the web are the same, we equate them to get a relationship between the P flange and P web. We then find the maximum torque that the flange and web can withstand. We are given the maximum stress, so using the equation of tau max, we can find out the maximum torque that can be applied in the flange. Similarly, we can find out the maximum torque that can be applied in the web. We now check which fails first. So consider the torque that the web can withstand. We multiply this torque by the ratio. We see that the value that we will get is greater than the torque that the flange can withstand. So in this case, the flange will fail. Next, we take the torque that the flange can withstand and divide it by the ratio. And we find that the torque in the web will be less than the torque that the web can withstand. Hence, the web will be safe. So the maximum torque in the flange governs failure. We have already found out the torque in the web by dividing the torque in the flange by the ratio. The total torque is given as twice the torque in the flange plus the torque in the web. We can use any of the equations of angle of twist. We have, for in this equation of phi flange, we have already found out EF. So we can find out the angle of twist of the whole I section.